Hello everyone, welcome to IIT and Gate classes. This is lecture 19 on TOC, and in this lecture we are going to start third topic according to syllabus of your chapter 4, that is Turing machines and decidability. Okay, so this topic is Church-Turing thesis. So let me read the statement of Church-Turing thesis. It says what could naturally be called as effective procedure can be realized by a Turing machine. So what does this statement means? This statement means that if for any problem we are able to write a procedure, then for to implement that procedure, we should have a Turing machine. Okay, so I have already written the statement. See here carefully. This means that for any problem, if we are able to design a procedure, okay, if for any problem, if we are able to design a procedure, then to implement that procedure we must have a Turing machine. Okay, so this procedure is a new term for you. So let me describe this term in next slide. Okay, so algorithm or procedure, many books says that these two are same thing, but actually there is a small difference between them. So let me read the statement for you. See, uh, roughly I can say algorithm or procedure is step by step process to solve any problem. Okay, so I think by now you already know about algorithm. You have already studied the definition of algorithm in data structures and algorithm subject, and we simply say that it is nothing but a step by step process to solve any problem. Okay, so we have a problem. Okay, so let me show you something. We have a problem, and to solve this problem we write some step by step procedure, that some step by step process, that is known as algorithm, or you can say procedure. But there is a small difference between these two. What is the difference? Let me read it out for you. Procedure, so see, first let me read algorithm. Okay, so it is nothing but a special type of procedure which always halts and say yes or no. Okay, so in algorithm subject I think you have already studied that step by step procedure to solve any problem, and it must always halt. That means it must always say yes or no. Okay, if answer is yes, then it should always say yes. If answer is no, then it must always say no also. So both answers should come, that is yes as well as no, in case of algorithm. But in procedure you can say procedure is a generalized algorithm. Okay, procedure is a generalized algorithm, and it may or may not halt. Okay, so in case of yes, it will always halt, and in case of no, it may or may not halt. Okay, so that means for yes, procedure is bound to halt and say yes, but in case of no, it may or may not halt. That means procedure is free. For no case, procedure is free. That means it may halt or it may not halt. Okay, so let me give you some examples so that you get more clarity about what exactly is procedure and algorithm. So roughly, if I want to say roughly, I will say algorithm or procedure is nothing but step-by-step process to solve any problem. We have a problem and we want to solve that problem. To solve that problem, we write some step-by-step process, that is known as algorithm or procedure. But the main difference between these two is that in case of algorithm, it will always halt and say yes or no. But in case of procedure, it may or may not halt. Okay, so let me move to next slide and show you some examples. Okay, see here carefully. Problem one. First problem is given number is prime or not. So you will input any number and you want to know that the given number is prime or not. So what will you say? See, for this problem, I will obviously say that algorithm exists. How? Obviously, you can design an algorithm for it. How will you design? So if the given if the inputted number is n, so you will try to divide this number from 2 to n minus 1. Okay. If this number n is divided by any number between 2 to n minus 1, then we will directly say that the number is not prime. And if it is not divided by any number between 2 to n minus 1, then we will say that the number is prime. So we are getting yes and no both answers. Hence, and it will obviously halt and say yes or no. Okay, it will obviously halt and say yes or no. Hence, we have algorithm. Okay, and procedure is a generalized algorithm, na? So obviously procedure also exists. Okay, so directly indirectly I want to say every algorithm is a procedure. but every procedure is not an algorithm. Okay, so see here carefully. Every algorithm is a procedure. Every algorithm is a procedure, but vice versa not true. Okay, that means every procedure is not an algorithm. See here, this is a procedure. This is not an algorithm. Okay, I hope you are getting my point, because algorithm is a special procedure which always halts and say yes or no. Or procedure is a generalized algorithm which may or may not halt. So by definition itself, we can say that every algorithm is a procedure, but every procedure is not an algorithm. So I hope by this example you have got the clarity about we have algorithm for this problem. And let me clarify you one more thing. I have said this point roughly. That means if we have n, then you have to try. You will try to divide this number n from 2 to n minus 1. So obviously we need not go till n minus 1. We can go till n by 2 also. Okay. For example, 100 is the number. Then you should check divisibility of 100 till 50. Okay, we need not go beyond 50. Okay, because minimum quotient is 2. I think you already know these things. So this is the more improvisation or more improvement. And one more improvement or better should be, you should go till root n. Okay, so you should go till, best is, see, one betterment is go from 2 to n by 2. And the more better is, you should go till 2 to root n. Okay, you should go till 2 to root n. Beyond root n, we need not check. And proof of these things is not needed here. You will study all these things in aptitude only. Okay, so divisibility, for if you want to check that n is divisible by any number or not, so you should go till root n only. Okay, we need not go beyond root n. Okay, so I hope I have made the point clear to all of you. Okay, so for example, if you want to check divisibility of say 53. Okay, so you need not go till 25 or something. You will go till what? Square root of 53. Okay, so square root of 53 will be 7 point something. Okay, so you may go till 8. Okay, no need to go beyond 8 for checking of given 50 to check the 53 is prime or not. You will go till 8 only. I hope I have made the point clear. It was really not required here, but I have given you just information. Okay, for because as far as TOC is concerned, we just need to give an algorithm. That means which always halt and say yes or no. And I have given you already an algorithm which is saying that for n, you will keep on dividing till 2 to n minus 1. And if the number n divides between any number from 2 to n minus 1, then we will stop and say answer is no. That means it is not prime. But if the given number n is not divided by any number between 2 to n minus 1, then we will say that the given number is prime. Okay. I hope I have made the point clear to all of you. So firstly, I said from 2 to n minus 1, then I improved and say 2 to n by 2. Then I improved again and I say 2 to root n. Okay, I hope I have made the point clear to all of you. And it's not required. So till here for TOC, this is more than sufficient. That means you just give me one algorithm which always halts and say yes or no. That's it. So this is these improvisations are for algorithm subject only. Okay, for finding time complexity and so on. Okay, so let me not confuse you, and I'm jumping to the next problem. Problem number 2, given number is perfect or not. Okay, so what is a perfect number? See, perfect number, for example, let me show you one example. 6 is a perfect number. Why? Because the sum of its factors. Okay, let me show you factors of 6. 1 less than 6. Factors which are factors of 6 which are less than 6. Okay, so 1, 2, and 3. Okay, these are the 3 factors for 6. So what will I say? I will say see, 1 plus 2 plus 3. That means sum of all the factors will be equal to number itself. Okay, that means what? This 6 is a perfect number. Okay, and so on. You can check it out. Other numbers also. And let me show you. I think 28 is also perfect number. Let me show you. 1 will be the factor of 28, obviously. Then 2 will be the factor. Then 4 will be the factor. Then 7 will be the factor. Any other factor? Okay, yeah, 14 will also be a factor. Okay, 7 to the 14 now. Yeah, so okay, 14 into 2 28, 7 into 4 28, and 1. Yeah, so 28 has all these factors which are less than 28. Okay, So sum them up. 1 plus 2 plus 4 plus 7 plus 14. What you will get? 7 plus 4, 11, 12, 13, 1, 14, 14 plus 14, 28. Yeah, 28 is also a perfect number. Okay, so how to find the factors? So for 28, you can do it like this also. Anyway, you are going to study them in aptitude, but let me show you here itself. 1. So immediately write 28 here. Okay, then 2, because 28 into 1 is 28. 2 into 14 is 28. Then 3, 3 is not 3 will not divide 28. Then 4, then 7 for the 28. That's it. Okay, so we are going to find the factors which are less than 28. So I will say that 1, 2, 4, 7, and 14. That's it. So these are all the factors of 28 which are less than 28. Okay, and we will sum them up and we will get 28 as our answer. Hence 28 is also a perfect number. So see here carefully, we are going till root n only. So 28, square root of 28 will be what? I think it will be approximately 5 now. So 5 point something. So maximum to maximum you can go till 6 and no need to go beyond 6. So I will say that 5. So 5 is not a factor, then 6 is also not a factor, and so on. So I will stop here and I won't go further. Okay, I hope I have made the point clear to all of you. So 1, 2, 4, then 5 is not the factor of 28, then 6 is not the factor of 28. That's it. You will not go beyond square root of 28 for finding the factors. Okay, I hope I have made the point clear to all of you. See here carefully. Okay, see here, we are not going beyond 6. Okay, that's it. And because okay, that's it, no need to go further. Okay, so given number is perfect or not. So what will be your algorithm? Algorithm will be very simple. Just find the factors. Okay, find the factors, and sum them up. Find the factors and sum them up. Okay, so how you will find the factors and so on, I'm not going into that much detail. I'm just giving you feeling that we can have algorithm for this problem which will always say yes or no. In case of yes, it will halt and say yes. In case of no, again it will halt and say no. That's it. So find the factors and sum them up. If the sum is equal, then you will say yes. If the sum is not equal to the given number, then we will say that the given number is not perfect. Okay, so find the factors less than n. Find the factors less than n. Okay, and sum them up. If the sum is equal, then we will say that answer is yes. If sum is not equal, then we will say answer is no. Okay, so I'm not writing it, I'm just dictating. You can note it down because our concern is not algorithm here. Our concern is that we have an algorithm. That's it. You should get a feeling that we have algorithm. That's it. So obviously we have algorithm. So obviously every algorithm is procedure. So we have procedure also for this problem. Okay, yeah. Now let's jump to the next problem. Please note it down carefully. Problem number 3. Find a perfect number greater than the given number. See, this is a very, very important point. We want to find a perfect number which is greater than the given number. So we will give any number n. So you need to find a perfect number greater than n. So can you guarantee that we will be able to find a perfect number greater than n? No, we cannot guarantee. Okay. So in case of yes, it will always halt and say yes. See, always halt and say yes. See, this is your perfect number. That's it. So output will be the given output will be a perfect number which is greater than the n, strictly greater than n. In case of yes, it will always halt and say yes. But in case of no, it may not halt. Okay, it will keep on checking. So if the given number, if the inputted number is 100, so you will keep on checking 101 is perfect number or not, 102 is perfect number or not, 103 is perfect number or not, dot, 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 dot. So you may not be able to find a perfect number also. Okay, so hence for this problem we have a procedure, but we do not have any algorithm. So I hope I have made the point clear. So procedure is just like algorithm only, but the only thing is it may or may not halt. That's it. Okay, so I hope I have made the point crystal clear to all of you about algorithm and procedure. Okay, so next is so this is all about Turing thesis. Okay, so let me remind you and say you something. So see again, Turing thesis is what? Now read. Now you will get the answer. What could naturally be called as effective procedure can be realized by a Turing machine. That means what? If for any problem we are able to write a procedure, then to implement that procedure we have a Turing machine. That means on Turing machine we can implement that procedure also. So roughly, I can say like this also. For any problem, you are able to design algorithm. Now you implement that algorithm in a form of a program. in and you run that on your computer. Okay, roughly I can say computer is just like a Turing machine only. Okay, so again I will repeat all these things in the subsequent classes, but let me give you small idea or small hint so that you get crystal clarity about Turing thesis. So if you are able to write an algorithm for any problem, then that algorithm will be implemented as a program and you can run that program in your computer. Okay, so computer is just like a Turing machine. So similarly, Turing thesis is saying that if you are able to design a procedure for any problem, then that procedure can be implemented on a Turing machine. Okay, I hope I have made the point clear. This is all about Turing thesis. Okay. Now we are jumping to some variations of Turing machines. This is your fourth topic according to syllabus of your fourth chapter, that is Turing machines and decidability. Okay, so this is fourth topic, that is variation of Turing machines. First is multi-track Turing machine, next is one-way infinite tape, next is multi-tape, next is Turing machine with stay option, next is non-deterministic Turing machine. So there are lots and lots of variations of Turing machines, but this is a basic course, so that's why I'm not going into detail of many variations. I will just concentrate on these 5 variations, and these are very basic variations. Okay. Yeah, so first is multi-track Turing machine. What exactly is multi-track Turing machine? See here, uh, standard Turing machine has only one track. Okay, so I have already told you Turing machine consists of tape of infinite length divided into cells. One cell store one symbol at a time. We have a read write head, okay, which is positioned to the first symbol of input string. Uh, okay, and except for some finite portion, rest of the symbols are blank and so on. Okay, I have already told you all these things. So this is a standard Turing machine. But what about multi-track? Multi-track means like this. Okay, so we have multiple tracks. We have multiple tracks like this. Okay, so here we can write A, B, A, here A, B, C, B, A, and so on. Okay, so we can write multiple symbols. Okay, so this is one track. See here, this is one track. So this Turing machine is having multiple tracks. Okay, so read write head on a single go, on a single, you can say, it will read all these symbols in a single move. Okay, so we will say that, see, initially Q naught. So we will say that Q naught, on Q naught, A, B is read. So now what will be the move and so on. Okay, so I can say that we will move to Q1 and A will become, say, B. Okay, so are you able to visualize it? We are reading all these symbols at a time, triple 4 A's and single B at a time. And now we are, see here, we will say, na, if we are at Q naught, so what will you say? Let me draw it properly for you. Okay, so what will you say? On Q naught, A is read. So our transition function was delta Q naught A. We will say that Q1 B R and so on, like this, na. So here what you exactly going to say? On Q naught, A B is read. So that means what, like this, na? 4 times A and B. This is read. So where will you go? We will go to Q1 and say, example, this A will become B, this A will become C, this A will become, say, D, this A will become, say, A. So A will remain A as it is, and this B will, say, become C. Okay. Now, and it will move towards read write head will move toward left or right. It's your own choice. Say, let's say it move towards right. So I hope I have made the point clear. Anyway, we are not going into details because this is a basic course. Okay, and it's not advanced course. In advanced course, I will say some more things about it also. But let me keep it simple here. Okay, so this is your multi-track, and power of both these. I think you will say that power of this will be more. Na, this will be more. But it has been properly proven that power of this multi-track and single track is exactly same. So you may argue that how can you say like this, because we are reading multiple symbols and so on, but it's hardly matter to me. Let me show you something. Okay, so I can implement the same thing with the help of single track also. So let me say you something about it. Okay, so see here carefully. This is your single track, or you can say standard Turing machine. So here I will write A, B, A. Okay, now after one or two blanks, I will write this double A, B, because tape is infinite now, so I can extend it. Now next I will say A, B, C. After blank I will say A, B. After blank I will say B, B, A, and then I will have blanks dot 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 dot. Okay, yeah. So now read write head Q naught, it will read this symbol A, then it will move forward. After blank it will read this A, then after blank it will read this A, then after blank it will read this A, after blank it will read this B, and so on. Now it will decide that where it will go, and so on. Roughly I have said you, and this is more than sufficient. So the main thing is, or the crux is, that these two have equal power. Do not think that multi-track will have more power than your standard Turing machine. That's such. Okay. So let me move to next slide. Please note it down carefully. I have given you rough idea. Okay. Yeah, please note it down carefully. I'm jumping to next slide. One-way infinite tape Turing machine. One-way infinite tape means what? See, standard Turing machine has two-way infinite tape like this, but I am saying one-way infinite tape like this. So you may think that two-way infinite tape will have more power than one-way infinite tape, and it's obvious thought also, but actually both have same power. How will you prove it that both will have same power? See, I will say that in this Turing machine, you just cut it somewhere. You just cut it because it is infinite in both the directions. So just cut it from here, from any cell. You can cut from any cell, and you just place it, place this part below it. So what you will get? So I hope you are getting my point. Like this, you will get like this. So now, if this symbol is A and this symbol is B, so here we will have A and here we will have B. Okay. So now, if you are going here, then you will go like this. Okay. So if you want to go in the left, then here you will go in the right. That's it. So, and I have already told you that multi-track and single track will have same power. So directly and indirectly, I will say that both will have same power. This is rough proof. Of course, it is a basic course. I'm not going into detail. I'm telling you again and again. I'm just giving you rough idea that both will have same power. You may think that single way infinite will have less power than two-way infinite tape, but no, it's not the case. I have given you a rough idea about just cut the tape somewhere, and then you just apply this part below it, so you will get like this. So if you want to go left here, because there is no way to go left here now, so what I will say that you want to go left here, then you jump to the next track and go left, and go right. Okay, so here if you are going right, that means here you are going left. That's it. So it's a rough proof. I'm not going into detail. Okay, yeah, please note it down carefully. I'm jumping to next slide. So the main thing is one-way infinite tape or two-way infinite tape. Two-way was standard Turing machine. One-way is your modified Turing machine. Both will have same power. Next, multi-tape Turing machine. Multi-tape means what? See here. Okay, this is one tape. This is second tape. This is third tape. You can have many tapes. Okay, so and each tape will have its own read write head like this. Okay, yeah. So now obviously you will say, sir, multi-tape is more powerful than single tape in a single tape Turing machine, which is your standard Turing machine, because obviously it is having one tape and it is having three tape, so it will be 3 times more powerful than this. No, it is not the case. I will roughly show you that this and this will have same power. How I will show you. See, I will say, because it is having 3 tapes. So let me take a Turing machine, multi-track Turing machine, which is having 6 tracks. Okay, 1, 2, 3, 4, 5, and 6. Okay, so 1, 2, 3, 4, 5, 6, and sorry, 7. I have got 7. So let me take 6 only. Okay, yeah, 6 track Turing machine, and the first track will act as this tape only. Second track will act as position for the read write head of the first tape. Okay, so let me show you here A, B, C. Okay, and here we have A, B, A, and here we have B, A, C. Okay, like this. Okay, so what I will say here we have A, B, and C. Okay, so the first track will be your like first tape, and read write head position is at B. So I will place a X here. Okay, yeah, for the next track I will say A, B, A, and I will place X here, and for this B, A, C I will place X here. That's it. So I hope I'm not going into detail now, and you have got intuitive idea that multi-tape and single tape will have same power. Okay, so in the one go we will change the symbol and so on. Please, I'm not going into detail, I'm just giving you an idea. That means what? We have got this multi-track Turing machine, and I have already told you multi-track and single track will have same power. So obviously multi-tape and the single tape will have same power, because these three tape Turing machine can be simulated by your multi-track Turing machine. That's it. This is more than sufficient for you. Okay, yeah, please note it down. I'm jumping to next slide. Okay, so I hope you have got the hint. For this basic course, this is more than enough to say that multi-tape and single tape or standard Turing machine. Standard Turing machine is a single tape, na? So multi-tape and standard Turing machine both will have same power. For this basic course, this is more than sufficient. But I have given you intuitive idea about why multi-tape and single tape will have same power. Okay. So I hope I have made the point clear. Please note it down carefully. I am jumping to next slide. Yeah. Next is Turing machine with stay option. So this Turing machine stay option means, see, we write delta Q naught A. So we say that we are jumping to Q1 B R. So that means what? A Q cross tau implies Q cross tau cross D. This was your delta for your standard Turing machine. So direction D can be either left or right. But with stay option is saying that direction can be either left or right or nowhere. That means you can stay wherever you are. Okay, that means it's not compulsion to go to left or right and so on. So, and it has been properly proven that Turing machine with stay option and Turing and standard Turing machine both have same power. Okay, standard Turing machine STM, standard Turing machine STM, and Turing machine with stay option both will have same power. Okay, Turing machine with stay option. Turing machine with stay option both have same power. Okay, please, very important point. You may get confused, so please note it down carefully. Okay, I'm not going into details, proof and so on. I'm just saying you that both will have same power, or roughly you can say if you want to give stay option on any state, then make it as a final state or make it as a whole state. This is more than sufficient. Okay, so in one word I have given you proof that both will have same power. Okay, so Turing, roughly I want to say that Turing machine with stay option means that intermediate state, on intermediate state also we can have a stay option. Okay, but in standard Turing machine only final state or halting state was having directly indirectly stay option. So so roughly I will say that yeah, if you want to make a stay option, if you want to give a stay move for non-final state, then make it as a halting state. Okay, so or do not apply a move. That's it. So see, these are our rough things, and I know that you may not be able to get it, but this is a basic course. For basic course, this is more than sufficient for saying to say that standard Turing machine and Turing machine to stay option have same power. That's it. This is more than sufficient. Okay, let's move to next, non-deterministic Turing machine. Non-deterministic Turing machine means that, see, we say that Q cross tau implies Q cross tau cross D. This was the delta for your standard Turing machine. But for non-deterministic Turing machine, we can have more than one move also. That means Q cross tau implies 2 power Q cross tau cross D. Just like NFA DFA. For DFA, what we have Q cross sigma implies Q. For NFA, we have Q cross sigma implies 2 power Q. Similarly here, for standard Turing machine, see, this is very important point. Your standard Turing machine is deterministic. It is not non-deterministic, it is deterministic. Standard Turing machine is deterministic, but Non-deterministic Turing machine is a modification of standard Turing machine. So it is modification of standard Turing machine. Okay, but I'm not going into proof obviously, but because this is a basic course, so I will directly say that deterministic Turing machine and non-deterministic Turing machine both have same power. Both have same power. The only thing is, okay, let me say it for you. Actually, I was trying to avoid it, but point is very important. So you should know about it. If a deterministic Turing machine is taking exponential time to solve any problem, then the same problem may be solved by non-deterministic Turing machine in polynomial time. Or in the sense I can say, if non-deterministic Turing machine is taking polynomial time to solve any problem, then the same problem can be solved by deterministic Turing machine in at most exponential time. Okay, so please note this point very carefully. Okay, so you can think of non-deterministic Turing machine as a magic machine. Okay, so magic in the sense, if it takes polynomial time to solve a problem, then deterministic Turing machine will take exponential time to solve the problem. It may take exponential time to solve the problem. Okay, I'm not writing these points because these points are covered in detail in advanced course. I'm just giving you a hint, or you can say idea. So the basic idea here is both have same power, but time taken to solve the problem is different. Different in the sense, if non-deterministic Turing machine is taking polynomial time, then deterministic Turing machine can take up to exponential time. Okay, yeah. So that's it. Or in the reverse fashion, I can say deterministic Turing machine is taking exponential time, then non-deterministic Turing machine may take polynomial time also to solve the same problem. Okay, that's it. This is more than sufficient, and both have same power. Please note it down carefully. These points, please note it down carefully. Yeah. So this is all about variations and summary. In the summary, I can say, okay, so in the summary, I can say, in summary, we can say that any modification, as we have already seen, we have seen 5 modifications, but actually we have lots and lots of modifications of standard Turing machine. So in the summary, I can say that any modification of standard Turing machine, STM, standard Turing machine, is not powerful, than STM. Okay, any modification of standard Turing machine is not more powerful. Okay, is not more powerful than your standard Turing machine. So standard Turing machine, actually it was invented by Alan Turing. Let me say you some brief introduction. A standard Turing machine was invented by Alan Turing in 1936. Okay, and he called that machine as computer. He called that the machine as computer because nobody give name itself, because it's just kind of arrogance, na, that you say that see, this is my machine, so I will say that see, if my name is Amit, and I will say that this is Amit machine, so it's not good, na, because it will show some arrogance. So to keep things simple, or Alan Turing was very humble person, so he didn't say anything that this is my machine, so I will say it as Turing machine and so on. So he said that machine is a computer, and he invented in 1936. Okay, and after a few years, the name was given as Turing machine. After this, the name of this scientist. Okay, and see, in 1936, this machine was invented, and after that, lots and lots of research have been done, but none of the machine is more powerful than your actual Turing machine, which was invented in 1936 by Alan Turing. Okay, so I hope I have made the point clear. Isn't it amazing, now? See, in 1936, Alan Turing invented the machine and named it as computer. And in 1936, nobody knows about what exactly is computer and so on. It was invented around 10 years after Turing machine in 1946, around 1946. Alan Turing, the Turing machine was actually, you can say, implemented mechanically. See, actually, Alan Turing also implemented it mechanically, but stored program concept and so on, von Neumann architecture came and so on. After 10 years, you can say roughly after 10 years, proper, you can say, computers were invented. Okay, and all these computers are just your implementation of your standard Turing machine only. The only difference is standard Turing machine is having infinite tape, but your actual computer is not having infinite memory, because infinite is nothing. It is a simple concept. So it is having finite memory only. And your standard Turing machine was sequential access, because after reading one symbol, then you can move left or right and so on. But computer is random access. So only we have these two differences. Rest everything is same. Or you can say that your modern computer is implementation of standard Turing machine only. So standard Turing machine is a model, and this model was implemented in the form of computer. So I hope I have made the point clear to all of you. So in 1936 itself, Alan Turing said that, see, isn't it amazing that computers were not invented, and in 1936 itself, Alan Turing declared that what exactly Turing machine can do and what it cannot do. Don't worry about what I'm saying. I will tell you in detail in subsequent lectures, that Alan Turing said that what Turing machine can do and what Turing machine cannot do. Actually, Alan Turing invented the Turing machine to show that logic is incomplete. That means with the help of logic, we cannot prove everything. Okay. See, logic is used to prove something, na? Something is true or false and so on. But Alan Turing said that with the help of logic, we cannot prove everything is true or everything. We cannot prove everything to be true or false. Okay. If you have some question, then, or if you have a problem, then with the help of logic, you cannot prove that this solution to the problem is yes, or solution to the problem is no, and so on. I'm talking roughly. Okay, I'm talking just roughly to give you some idea, or you can say to give you a clear picture about what why that Turing machine was invented. So Alan Turing invented a Turing machine to show that logic is incomplete. That means with the help of logic, we cannot prove everything. Okay, so so Alan Turing invented the Turing machine to show all these things, and directly and indirectly, Turing machine will have lots and lots of limitations. So Alan Turing said that what could naturally be called as effective procedure can be realized by Turing machine. That is Church-Turing thesis. So Church-Turing thesis indirectly saying that logic and Turing machine have same power. Okay, that means what can be done logically can be done by Turing machine. Okay, so the amazing part is that in 1936 itself, Alan Turing said that what computer can do and what it cannot do. And actual computers were not invented till now. After 10 years, the actual computers were invented. But in Alan Turing, before 10 years, said everything about computers, that what they can do and what they cannot do. Isn't it amazing? Okay. Yeah, so that's it. So okay, so let's move to the next slide. Okay, I'm not going into more details, okay, because this is a basic course now. This is not an advanced course. Okay, so please note it down carefully. Okay, so next topic is your RE and REC languages. Okay, so it was your fifth topic. Sorry, I think we have covered 4 topics now. Yeah, fourth topic was variation of Turing machine according to your syllabus. Now we are jumping to fifth topic according to your syllabus, that is RE and REC languages. Okay, now see here carefully. What exactly is RE language? Let me read it out for you. A language is said to be RE if and only if, please note it down carefully, if and only if, that means both directions, if and only if there exists procedure to check W belong to L. Okay, so we have a language. Language is what? Set of strings, and we have an arbitrary string W. We want to check, see here carefully, we have a language L. Of course, it may be infinite language also. And we have a string W. We want to check this W belong to L. And for checking this W belong to L, we have a procedure. If we have a procedure, then the given language is said to be RE. So procedure means what? In case of yes, it will always halt and say yes. But in case of no, it may go to loop also. Okay, it may not say no. That means it may not halt. It may not halt means it may go to infinite loop. So what I'm saying is, if W belong to L, then it will always halt and say yes. But in case if W does not belong to L, then it may not halt. So that directly I'm saying that it may halt or it may not halt. That means it may go to infinite loop. What exactly it here? It is nothing but Turing machine. So finally, okay. So let me say you another definition, then I will come to this point. Don't worry about it. Okay. So or another way can be a language is said to be RE if and only if there is a Turing machine accepting it. So I have already told you about Church Turing thesis. So what was the statement? What could naturally be called as effective procedure can be realized by Turing machine. See, I am saying this line again and again because in your if you get a good rank in GATE, then you may get selected in MTech for in old IITs or any premier institute. So you may face some interviews also, and in interviews, professors' favorite question is Church Turing thesis. Okay, I am not saying this. My experience is saying it, and I am teaching this subject from the past 12 years. And many students have told me about this fact that sir, you told us about Church Turing thesis, and the same question was asked by our professors in our interviews. So please note it down carefully. Church Turing thesis says what could naturally be called as effective procedure can be realized by a Turing machine. Okay. So so what could naturally be called as effective procedure can be realized by Turing machine. That means what? If we have a procedure, then we should have a Turing machine to implement it. So directly and indirectly, I am replacing this procedure word with Turing machine. Okay, so a language is said to be RE if and only if there is Turing machine accepting it. Now come to this point. Now you will understand it properly. So if W belong to L, then Turing machine will halt and say yes. But if W does not belong to L, then Turing machine may not halt. That means it may halt and say no, and it may not halt also. That means it may go to hang state also. Or hang means what? Silently discard it. Okay, or silently say no. Okay. So I hope I have made the point clear to all of you. So Turing machine is free. So restriction on Turing machine is that in case of yes, it will halt and say yes. But in case of no, it is free to hang also. Okay. So see here carefully. I have written the line also. So acceptance here means that we care about members only. Okay. So we care about members means what? For members, we have to say yes. Okay. But for non-members, we are not concerned. That means it is free to say no, or it may go to hang also. I have written also about members only. That is, for members, Turing machine will halt and say yes. But for non-members, it's free to say no or go to hang. Hang means what? Silently say no. Hang means silently say no. What exactly is hang? I have already told you in the previous class. Please watch that lecture. Okay. So hence RE languages, see here carefully the next point. Okay. So I have written hence RE languages are also known as Turing recognizable languages. Turing recognizable means what? A Turing machine can recognize these languages. Recognize means it can recognize the members. Recognize means Turing machine can recognize members. Turing machine can recognize members. For non-members, it is free to say no. That means Turing machine may halt and say no, and or it may go to hang also. Hang means it will silently say no. Okay, I hope I have made the point clear to all of you. So let me revise you everything. So what exactly is RE languages? A language is said to be RE if and only if there is a procedure to check string belong to L. Or another definition can be procedure means what? Turing machine. So procedure means what? According to Church Turing thesis, if we have a procedure, that means what? This procedure can be implemented on Turing machine. So roughly I can say procedure and Turing machine are equivalent things. So that means what? A language is said to be RE if and only if there is Turing machine accepting it. So if the language is accepted by Turing machine, then we will say that language is RE. That's it. Just like regular, we say that language is regular if it can be accepted by finite automata, and a language is said to be CFL if it can be accepted by PDA. So same fashion, I am saying that language is RE if it can be accepted by Turing machine. That's it. Okay. So here, so accept here means what? We care about members only. That means for members, Turing machine will halt and say yes. But for non-members, it's free to say no, or it may go to hang. So hence RE languages are also known as Turing recognizable languages. That means Turing machine can recognize these languages, or you can say Turing machine can recognize the members of the language. That's it. So I hope I have made the point clear. Please note it down. I will put everything on one slide so that you can note it down carefully. Okay, yeah, please note it down. And what exactly are RE and REC languages? I think I have not given you full form of these. So let me give you full form also. Okay, so okay, so now I'm writing RE means what? Recursive enumerable languages. RE means recursive enumerable languages, and REC means recursive languages. REC means recursive language. RE means recursive enumerable languages. Enumerable means enumeration. Enumeration means listing. So you can list their members. Okay, if you are able to list the members of your language, or you can say list all the strings, then we will say that languages are. Okay, and REC means recursive. RE means recursive enumerable. Okay, so let's move to next slide. Next is REC languages. Okay, so about RE, I have said many things. So let me show you something about REC. See the definition. A language is said to be REC if and only if there is this algorithm to check W belong to L or not. I am saying here not also. See here, I have not said not. W belong to L only. No, because procedure cannot say no. Procedure may or may not say no. Okay, so I have not written or not, but here I have written not also. That means what? We care about members as well as non-members. For members, it will say yes. For non-members, it will say no. Yes and no, both answers should come. Okay, so this is the basic meaning of algorithm. Because I have already told you, algorithm and procedure are different thing. Algorithm means which always halts and say yes or no, and procedure means it will always say halt and say yes, but in case of no, it may not halt. So that this is the main thing. Okay, so language is said to be REC if and only if there is this algorithm to check W belong to L or not. Okay, or in another way can be a language is said to be REC if and only if there is this halting Turing machine accepting L. HTM means halting Turing machine. So what exactly is halting Turing machine? As the name implies, halting means what? It will always halt. Okay, so halting Turing machine is a special kind of Turing machine which always halt. So see here I have written HTM never hangs. Directly and indirectly I am saying HTM never hang. That is, HTM is a special type of Turing machine. HTM is a special type of Turing machine which halt on every input. Okay, so no matter whatever input you give, it will always halt. So that means hanging is not allowed in HTM. Okay, yeah. So see here. So another you can say, we can also say that REC languages are also known as Turing decidable languages. What we said about RE were known as Turing recognizable languages. And what about REC? We are saying them as Turing decidable language. Decidable means what? We are able to decide that whether the string belong to language or not. That means what? W belong to L or not. In case of yes, it will always halt and say yes. In case of no, again it will always halt and say no. So decidable means what? Yes and no, both answers are coming. That's why we calling them as Turing decidable languages. Okay. So I hope I have made the point clear to all of you, and I have put everything on one slide. Please note it down carefully. This is all about REC languages. Okay. So see here, since HTM is a special type of Turing machine, halting Turing machine is a special type of Turing machine. That means every halting Turing machine is Turing machine, but vice versa is not true, because Turing machine is free to hang. That means hanging is allowed in Turing machine, but hanging is not allowed in halting Turing machine. So halting Turing machine is a special type of Turing machine, na? So hence we will say what? Every halting Turing machine is a Turing machine, but every Turing machine is not halting Turing machine. So let me say you here, every halting Turing machine is a Turing machine, but vice versa not true. And halting Turing machine corresponds to what? REC languages. Okay, and Turing machine corresponds to what? RE languages. So directly and indirectly, what I will say, that this is very, very important point. Please note it down carefully. Every recursive language is RE. Every recursive language is recursive enumerable, but every recursive enumerable is not recursive. Okay, so please note it down carefully. So okay, so I have written here also See here carefully. Hence, every REC is RE, but vice versa not true. Let me say it again. Since halting Turing machine is a special type of Turing machine, that means every halting Turing machine is Turing machine, but vice versa not true. If you are not able to get it, please rewind the video and watch it again. Otherwise, video will be very lengthy. I'm not going to repeat again and again. You will get irritated also. So every halting Turing machine is Turing machine, but vice versa not true. So halting Turing machine and Turing machine. This will be your Venn diagram for this thing. That means if you collect all the halting Turing machine in this world, we are considering it as a set, and you consider all the Turing machines in the world, that will be this set. Okay. So I'm showing it by Venn diagram. So halting Turing machine correspond to what? REC languages. Turing machine correspond to what? RE languages. So every REC will be RE, but every RE is not REC. Okay, please note it down carefully. Yeah. So that's it. So let me keep things very simple, and I'm stopping this lecture here itself. So in the next lecture, I will move to some more things. So the basic idea will be, in the next lecture we are going to study closure properties of RE and REC languages. Closure property, I have already told you about union, intersection, set difference, concatenation, transpose, and so on. So we have around 8 to 9 closure properties, and we will study all these closure properties in detail in the next lecture itself. Okay, and subsequently we will jump to next topics of your this chapter. Okay, yeah. So thank you so much. Bye bye.